Greetings, math fans. Alright, so this is day 3, and we're going to talk about something called the sandwich, or sometimes they call it the squeeze theorem. Alright, and before we get started, I'd like to mention a little word from our sponsors, which is Sandwich Theorem is brought to you by Burger King, and the Squeeze Theorem is brought to you by this lovely teddy bear. It says, "I love you." Oh, that's so nice. All right, let's get back to the lesson. Sorry, that was pretty bad. Okay, so the sandwich or squeeze theorem, basically, if we can't find a limit directly, we can find it indirectly using the sandwich theorem. All right, and what I mean by we can find it indirectly is this. It refers to a function whose values are sandwiched between the values of two other functions. Okay, and basically what you have, math fans, is if I can find the limit, if I have two other functions and I can find the limit of those two other functions, that means that limit of the one in between is going to be, the limit's going to be between those two functions. So if I can actually establish the limit to be the same for the left hand and the right hand side, and if it's the same, then that function in the middle has to also be the same. Okay, so let's call the original function, just an example. If the original function is f, and the functions on either side, so functions on either side of f are g and h. Alright, we can say that the limit as x approaches c of g, if these limits are the same, limit as x approaches c of h, right, that function is going to be limit as x approaches c of f, that is going to be between those two functions. Okay, we just need to establish that. So let me kind of start out with an example. But if these two are the same, then that would be also the same value. So if let's say this came out to be 105, and this came out to be 105, my favorite number, that means that would actually be equal to 105, right? Because if it's between 105 and 105 with an equal to sign, then it's actually got to be equal to that value 105. So let's do a nice little friendly example here. If I said limit as x approaches 0 of 3 plus 2x times cosine of 1 over x. Okay, and I want to find that limit. Well, math fans, you can't do it directly because you'd have 3 plus, if I did direct substitution, I get this, right? And you can't have that. That's bad. So what I need to do is I need to use sandwich theorem and think about what is the smallest value that can be. And when I say that, I mean the whole thing. What is the smallest thing that cosine of something can be? Don't you guys agree that cosine is between -1 and +1? So the smallest value that can be is -1. So let's write it out as 3 plus 2x. I'm going to leave that as an x times -1, because that's the smallest value. And that is going to be, my other function is 3 plus 2x cosine of 1 over x. And then the biggest value this can be is 1, so I'm going to put this on the right hand side, 3 plus 2x times +1. Okay, that makes sense, right? because again, that's the smallest value, that's the biggest value, so it's got to be between that. Now let's take the limit of each one of these, because now I can actually take the limit as x approaches 0 of 3 plus, or actually it's going to be 3 minus 2x. You guys agree with that? And that limit is equal to, well, it's just direct substitution. 3 minus 0 is 3. Okay, and 3 plus 2x cosine of 1 over x. And let's do the same thing here. Limit as x approaches 0 of 3 plus 2x. Well, again, I'm going to do direct substitution. Don't you guys agree that's equal to 3 plus 0 or 3? So now I can say that this limit is equal to 3. This limit is equal to 3. And so this limit as x approaches 0 has got to be between that. It's a sandwich theorem. So if they're both 3 on either side, this also has to equal 3. Okay? That's kind of how the squeeze theorem or the sandwich theorem works. Let's take a look at our graphing calculator really quickly and just kind of graph it. So if I do y equals, and let's just stick our original equation in. It's going to be 3 plus 2x cosine of 1 divided by x. Okay, and let's do zoom 6. Okay, so what I'm trying to do is I'm saying, what does it look like in here? Now, if you look, because I have a nice bigger picture over here, right, I kind of see it's got something weird going on here, right? It's kind of like going up, and well, of course, you know, cosine oscillates up and down, and that's kind of what's going on here. I can zoom in a little bit closer. Let's actually change our window instead of zooming. We can change our window to, it looks like y is going to be between, let's do between 0 and 5. Get a nice little close-up view, and we can graph it. And we can see again what's going on here, right? Something's going on in this area. Let's actually do calculate. Second calculate, and let's do a value. So we know it's as it's approaching 0. So obviously if I type a 0 in, what am I going to get? Well, see how it says y equals and there's nothing there? Well, that's because it's not defined there. I can't do a direct substitution. That makes sense because you can't have cosine of 1 over 0. So let's do that same thing and second calculate. So let's calculate a value for negative 0.00000001, and what do we get? 3.0002. So that's coming from the negative side, and obviously we put positive. So let's do second calculate. We do value positive 0.000001. Let's see what we get. 2.999998. Okay, so we can see that it is approaching 3. Now you're like, well, Mr. Carpenter, why don't we just use our calculator all the time? Why are we using the squeeze theorem? Isn't that kind of silly to do that? Well, first of all, we're going to get an exact answer when we use the squeeze theorem. Second of all, if you're in your AP exam and this is the non-calculator part, you're going to actually have to figure it out without a calculator. You're not going to be able to plug in a value, and it gets pretty tough to plug in 0.00001 into that function and come up with a reasonable answer. Alright, so that's where the squeeze theorem kind of comes in handy. Alright, so let's go back to and do another example here. If I said limit as x approaches 0 of x squared cosine of 1 over x squared. It's very similar to it, but it's okay. I want to do it. Alright, so again, you know, we're going to do the same thing. We know that our minimum value for this one is -1 and our maximum value is +1. So let's use the squeeze theorem. It's going to be x squared times -1 is going to be less than or equal to x squared cosine of 1 over x squared less than or equal to x squared times +1. Okay, so it's got to be those two functions. Let's rewrite this. This is negative x squared less than or equal to x squared cosine of 1 over x squared less than or equal to x squared. Okay, and now let's do the limit. So the limit as x approaches 0 of negative x squared equals 0. and the limit as x approaches 0 of positive x squared equals 0. So that means this guy right here, math fans, the limit, because it's between these two values, limit as x approaches 0 of x squared cosine of 1 over x squared, that then has to be between 0 and 0, which means that is then equal to 0. Okay, and if you look sideways, it's going, oh no! That's the right answer. All right? That's pretty reasonable. And you can do that, of course, for sine or cosine, which kind of makes sense, using the squeeze theorem for that, right? Because it's between -1 and +1. You know, you really can't use it for secant and cosecant because their values are from -1 to -infinity and 1 to +infinity. So, you know, sine and cosine are definitely great functions to use the squeeze theorem. All right, the reason we're using, even coming up with the squeeze theorem, or kind of showing you that, is because I want to talk about a function here. And the function I want to talk about is the limit, and we're going to use theta. Limit as theta approaches 0 of sine of theta over theta. Now, you can't just come up with an answer for that because you can't use direct substitution because of you know, theta. You can't have a 0 in your denominator; it will be undefined. So what we're going to do is we're going to use the squeeze theorem. Now I have some kind of pre-printed note sheet here that I made, and I'm showing you this here now just because it's going to look a lot cleaner if I don't draw it. So I've got two circles here, math fans, and they're both unit circles. Okay, so I'll highlight a couple things here. They're both unit circles. So they have a radius of 1. And what I want to do is I want to, again, talk about sine of theta over theta. And we're going to actually get to that, but we have to do a few things first, okay, to use the squeeze theorem. I want you guys to understand that this is, here's our x here. See our value of x? That's an arc length. Remember our equation back in the day? S equals, let's write that out here. S equals r theta. Well, when r is equal to 1 for this problem, isn't that x equal to that x? Because, of course, that's your arc length, right? So that establishes this guy right here, that x, and also the other circle, that x. Now, the reason I'm establishing that is because I want to show that that x is between that y value and that z value. So the y value for the first triangle and the z value for the second triangle. Notice I have two sets of right triangles. So let's look at the first unit circle. I have a nice right triangle here. And so I want to come up with a nice little function for y. Isn't sine of x equals y over r? Well, if r is equal to 1, so sine of x equals y, right? So that's my first function. I could cross multiply, or I could just say y equals sine of x. So that's my first function, y equals sine of x. And let's look at the next triangle. I have it in terms, I have a z, I call that's one side z. So if I take the tangent of x equals z opposite over adjacent, so z over r, well r again is 1, so I have tangent of x equals z, or z equals tangent of x. So those are the two things I just established here. That's pretty important. So y is equal to sine of x and z is equal to tangent of x. Okay? That x value is between, this is here, right here, just by the picture, the length of the x value is between the values of y and z. Alright? That's really important because now what we're going to do is we're going to kind of manipulate this a little bit. Well, let's substitute that in. We already know y is equal to sine of x and z is equal to tangent of x. So here it is. X is between sine of x and tangent of x. And I want to make a quick comment here, math fans. That's only when x is between 0 and pi over 2, right, in the first quadrant, right, for our arc length. All right, because if you start going into the other one, the arc length gets bigger if you go into the other quadrants. So now what I'm going to do is I'm going to manipulate this a little bit. I'm just going to divide every side here, or every one of those pieces of the inequality, by sine of x. So if I do that, I get 1 less than, and actually this should be less than, and I'm going to write this in here, less than or equal to, because we need that. Less than or equal to x over sine of x, less than or equal to sine of x over cosine of x divided by sine of x. All right, so I divided everything by sine of x and just wrote that sine of x over cosine of x as, or tangent as sine of x over cosine of x. So I can simplify now this guy right here to this. You guys okay with that? Right? And now I want you guys to understand, here I did the squeeze theorem. So now I did the limit. This is, let me highlight what I'm doing now. I'm taking the limit as x approaches 0 of 1, which of course is just 1. And I took the limit as x approaches 0, so this guy right here. Well, that I can directly substitute in because cosine of 0 is 1, so that's equal to 1. So they are both equal to 1, and if they're both equal to 1, that means what's in between is also equal to 1. And so this is what I've come up with. Limit as x approaches 0 of x over sine of x equals 1. That is so huge, math fans. All right, that is just amazingly huge. Now, I know some of you guys are saying, wait a second, Mr. Curvis, it was sine of x over x. Well, it doesn't really matter, especially when it's equal to 1. If it's like, 5 over 5, and I do the reciprocal of that, isn't that still 5 over 5? So it's equal to 1. So let me go back to my original problem. So that's done. We're done with the picture here now. But if I go back to the original problem, I can now say that this is equal to 1. Okay, so this is equal to 1. That is huge. That is so important. Got to memorize that, math fans. That is just a key thing. I mean, you could develop it each time, okay, but I don't think you want to do the squeeze theorem in the middle of a test when you're allowed 50 minutes to do a whole bunch of problems. So you got to have that memorized. Limit as theta approaches 0 of sine of theta over theta is equal to 1. Okay, but that's what the squeeze theorem is. Real quickly, I just want to show you with the graphing calculator. Let's clear this out of here, and let's do sine of theta. So we're going to do sine of, or x, right, divided by x. And let's zoom 6. So here it is, right? Let's zoom in a little bit more. You can see it on the picture below here. But if I zoom in a little bit more here, there we go. Okay, that's a better picture. So what happens when x or theta goes to 0? Well, it doesn't. It appears it's going to 1. Okay, so let's. I can't. Right? If I do second calculate value and I type in 0, what do I get? Of course, I don't get anything. Right? I shouldn't get anything because it's not defined there. But again, we're talking about a limit. What's going on as we get close to it? So let's put in second calculate, and let's put in point 00 value negative 0.00001. Look at that, man! It even shows 1 there. Sweet. And let's do second calculate, and let's do 0.00 on the other side, 0.001. Look at that, y is equal to 1, man. Okay, so it's getting closer and closer and closer to 1. That's what the limit is. Okay, so I just want to show you that on your graphing calculator. Alright, so let's keep going here. So that's an important concept to understand, the squeeze theorem, and to see where we actually got that from. I want to do 2 more different examples with you guys. The other one is limit as theta approaches 0 of cosine of theta minus 1 over theta. Alright, and again, you can't do direct substitution because you'd get, it would be undefined. So what I'm going to do is I'm going to manipulate this a little bit. I'm going to multiply this by cosine of theta plus 1 over cosine of theta plus 1. And on top I get cosine squared of theta minus 1. And on the bottom I'm just going to leave it as theta times cosine of theta plus 1. Okay, and if you guys remember from sine squared plus cosine squared equals 1, if I wrote cosine squared of theta minus 1, that's actually equal to negative sine squared of theta, and then over theta times cosine of theta plus 1, right? And then I can actually split that up to sine of theta over theta times negative sine of theta over cosine of theta plus 1. And now what I want to do is I can take the limit of, as theta goes to 0, of this whole thing, right? And again, the reason I rewrote that is because I've already established that sine of theta over theta is equal to 1. So let me just write this out. I can write this out. Limit as theta approaches 0 of sine of theta over theta times, and again, this is about my product rule. I can split it up, times limit as theta approaches 0 of negative sine of theta over cosine of theta plus 1. Okay, so that is equal to, well, this first guy is equal to 1 times, well, what can I do? Can I do direct substitution? Well, sure I can, because I can do that because negative sine of 0, don't you guys agree that's 0? And cosine of 0 is 1. Well, that's cool because I don't have a denominator that's 0, so I really have 1 plus 1. And of course, this guy right here, isn't that 1 times 0 over 2 or 0? So my answer is 0. So the answer to this whole thing, let me kind of write this out again. Limit as theta approaches 0 of cosine of theta minus 1 over theta, that's equal to 0. Okay? That is another important one, math fans. I would put some stars next to this one because you need to know this one. Alright? So let's do our last one. And that is going to be the limit as theta approaches 0 of tangent of theta over theta. Okay? Again, that's kind of complicated to try to use the squeeze theorem, but we're using what we established already with sine of theta over theta equal to 1. So I can rewrite this, and that's what I want to do, is I want to rewrite this in terms of sine of theta. So I can rewrite this as sine of theta over cosine of theta over theta, right? And so I can say that's sine of theta over theta cosine of theta. So now I can write this as limit as theta approaches 0 of sine of theta over theta times, right, I'm going to split this up as limit as theta approaches 0 of 1 over cosine of theta. You guys agree? I just split it up. Okay, I'm allowed to do that again by the product rule or product theorem. And then, of course, we already established this one. What is that equal to? It's equal to 1. And now I need to figure this one out. Well, of course I'm allowed to do this because it's defined. Cosine of 0 is 1. So it's times 1. 1 times 1 is 1. So there we go. Limit, let me write this out. Limit as theta approaches 0 of tangent of theta over theta is equal to 1. Okay, another important one. So I'd put a couple stars by this guy right here too. So we got 3 different theorems. We got our 3 different limits that I just showed. We have, let me just write this out. That's equal to 1. Limit as theta approaches 0 of sine of theta over theta. That's equal to 1. And then our last one, limit as theta approaches 0 of cosine of theta minus 1. And please be careful about that. Don't get that confused and write cosine of theta plus 1. It's cosine of theta minus 1 over theta, and that's equal to 0. Okay, the other ones are equal to 1, that one's equal to 0. So remember, 1 and 0. Okay, those are the 3 things that I want you guys to know for this day. We're actually, for our next lesson, we're going to be utilizing these 3 functions and then manipulating them to give us answers for a lot more different limits. All right, but that is, again, we established it, the sine of theta over theta, using the squeeze theorem, and hopefully you guys kind of understood the squeeze theorem a little bit. All right, that's it, math fans. Have a great day. Adios. Goodbye.